So welcome back. The essential of having a coffee or a tea is to do more. So our last speaker of the afternoon session is Professor Zhonggen from Zhejiang University, and he's talking about asymptotic fluctuations or random interpretation.
Thank you very much. It's a pleasure to be here. First of all, I'd like to thank the organizer for nice meeting. Today, I'm going to give a talk on limiting theorems for random integer partitions. This is the outline of my talk. First, I quickly review some notations on integer partitions, and then we define three kinds of probability measures on the integer partitions. Basically speaking, we look at two kinds of probability measures. One is multiplicative probability. The other is Plancherel probability. And then we look at their limiting behaviors. For example, limit shapes and asymptotic fluctuations. Let's begin with some notations about the partitions of integers. Suppose n is a natural number. A partition of n is a sequence of natural numbers, such that their sum is exactly equal to n. For simplicity and clarity, we assume this sequence of natural numbers is decreasing. N is called the size of a partition. L is the length of a partition number. Number I are called parts of partition. For example, n is equal to 10. There are many partitions of 10. For example, this is one, this is another one, this is another one. So a basic question is how many different partitions of 10 are there? You can count in mind. Okay. Another way of writing a partition number is as follows. Let Rk be the number of parts with equal to k. So the following identity is held. The sum of Rk is equal to the length of the partition. The sum of k times Rk is exactly equal to the total number of parts. So it's equal to n. So we can write lambda as follows. R1, just as the number of ones in the partition. R2, just the number of parts of 2, so and so on. It is also useful to use the Young diagram. What is the Young diagram? Young diagram is a geometric representation of a partition. Let's just look at these three pictures. These three pictures are often used in the study of partitions. Let's look at the first one. This is a partition, this is a Young diagram of partition number. The first row has number 1 boxes. The second row has number 2 boxes. The total number of boxes is n. So we also need a dual diagram. A dual diagram, number prime, is obtained by rotating the diagram of number along the diagonal line. In particular, denote the number prime by this. So according to the definition of dual diagram, number prime, number one, the first part of number prime is equal to the length of number. So number 1 prime is equal to L. The length of number prime is just equal to number 1. So the number prime is just the rotation of number along the diagonal. In the above, we give some notations about the integer partitions. Now let's consider the random integer partitions. Let the capital Pn be the finite space of all partitions of n. That is to say, the capital Pn is the set of all partitions of n. One can assign a probability measure P number to each partition from Pn. So we have a probability space. The goal of this talk is to study the asymptotic behavior of a typical random partition number under the probability measure P as the total number of partitions n goes to infinity. Yeah, so you can assign a probability measure as you like. In this talk, we shall particularly consider the following 3 probability measures. First one is the most natural one, is uniform measure PU, because capital Pn is a finite set, so we can choose a partition uniformly at random. Okay, and then the second one is a generalization of uniform measure. We call multiplicative measure. I will explain this term below. Okay, and the third one is the Plancherel measure. Let's give the detailed definition. Yeah, okay. Denote the small Pn is the number of capital Pn. Then we have the following numbers. Yeah, for example, if n is 10, there are 42 different partitions of 10. If n is 100, there are maybe 1,000,000,009. Yeah, okay. It's hard for me to count this number. Okay. You can imagine how many different partitions for general n. Pn is actually Pn is a well-known function called the Euler function. Actually, the study of partitions goes back to Euler as early as in 1750s. So, according to actually, Euler has got the following famous identity. Pn is a sequence of natural numbers, so we can induce generating function. This Pn, yeah, okay, Pn xn. This is the generating function of Pn, right? Euler got the following identity is equal to the product 1 minus x cube. Yeah, the product of 1 minus x cube. According to this identity, Harder, Namanuji, and Adamacher got the following asymptotic formula about the Pn. This is very famous in the history of integer science. So we define uniform probability measure PU by this. This is the most natural probability measure in a finite space. According to the definition, it is obvious that lambda and lambda prime have the same probability, which is just 1 of Pn. 1 of Pn. Okay. Now we extend the above uniform probability to general case. We need some parameter beta prime beta. Consider a sequence of functions. This function is analytic in the open disk. And then we make Taylor expansion. We got the Taylor series as follows. Its key of G is the coefficients of Taylor series. Of course, its key of zeta depends on the parameter beta. And then we define the probability measure Pm beta of lambda is equal to 1 of co-in. Is proportional to the product of its key of R key for any lambda in the set capital Pn. Lambda is written as this. So R key appear in the probability formula. This probability is called a multiplicative measure associated with the family of functions fk beta. This probability measure is also used in the statistical mechanics. This is a very early paper by a physics template. The title is Statistical Mechanics and the Partitions of Integers. He discussed this kind of probability measure, and in physics literature, this is referred to generalized Bose-Einstein statistics. When beta is equal to 0, if kz is very simple, is equal to 1 of 1 minus z. So all of its k of g is equal to 1. And then co-in is just the number of partitions. In this case, Pm0 is reduced to the uniform measure. But if beta is different than 0, is larger than 0, lambda and lambda prime have different measure. In this case, the Pm is different from the uniform. As you see, in the uniform case, lambda and lambda prime have the same probability. Next, let's introduce the Plancherel measure. For this, we need some more notations. Fix a partition lambda of n. Fix a partition lambda of n. You see, there are many different partitions of n. So now let's fix the one. And then we define a standard Young tableau. A standard Young tableau is defined as follows. We just put n different numbers into n boxes in such a way that the numbers increase along the roots, and the numbers increase down the columns. For example, this is a sheet, a Young diagram of the partition 5, 4, 1 of 10. Okay? And then we put 1, 2, 3, and so on, 10 into these boxes in the following way. These are two typical examples. A natural question is fixed number. How many different standard Young W are there for this number according to this way? Let D number denote the total number of all standard Young W associated with the number. It is given by the Hooker formula. D number turns out to be equal to n factorial over the product H. What is the H? H is the Hook length of this box in the Young diagram. Let's just look at this example. Okay? Let's look at the first box. This is the hook. This is the hook. There are totally 7 boxes in the right of this box, and below this box there are totally 7 boxes. Okay, so we just write 7 in this box, and so on. What is the D number for this shape, for this diagram? We just calculate by 10 factorial divided by 7 times 5 times 4 times 3 and so on. We get the exact number is equal to 288. Besides, we have the following simple identity. The sum of D number square over the set, over the space Pn is equal to n factorial. According to this identity, we can define the following probability measures. We just take the probability measure of lambda is equal to D lambda square over n factorial. You see, the total sum of this is equal to 1. So that is really a probability measure. In this way, we have another probability space. Okay? Under this probability space, the probability lambda and the lambda prime is again equal to each other. Now, next I want to point out the difference between PU and PP. There is a big difference between these two typical measures. For example, again, n is 10. So we have 42 different partitions. According to uniform measure, PU of lambda is exactly 1 over 42. Okay? But under the another space, PP, these partitions have a very, very small probability, just 1 over 10 factorial. But for this partition is under PP P means Plancherel measure. Okay. Under this, what is this? 4, 3, 2, 1. Is there are 4? Okay. 3, 2, 1. This partition has the largest probability 1/6. That means we have a very large probability to see this kind of picture. Okay. But yeah, under the uniform probability, this picture appears. It appears just with the probability 1/42. But under this probability measure, it has 1/6. It is much bigger than the uniform measure. Okay, next let's turn to limit shape. A remarkable feature in the study of random partitions is that there is a limit shape for each measures as n goes to infinity. We just need some notation about the limit shape, about the shape. Yeah, this is the mathematical definition. We don't let's skip this. We just look at the picture. Yeah, phenomena. What is the phenomena T? Phenomena looks like this. Phenomena T is the step function. Is the step function of the boundary. Is the boundary of this Young diagram. So it is non-increasing step function. It turns out that phenomena T under properly scaled looks approximately like a smooth curve. As n goes to infinity, the box becomes small and small. So the area of each box is just 1/n. N is the total number of partitions. And so there are n boxes, but each box has area of 1/n. So the total area is exactly 1 for each n. So this is the typical limiting shape. As n goes to infinity, under the uniform measure. Yeah, this is a mathematical description statement. Yeah, if you want to look at the picture, it looks like this.
So what's finite? What is finite?
Sign up.
Yeah, what is it?
Sign up. Oh, Plancherel is the famous curve. It was first obtained via a heuristic argument by Templer in 1949, but the rigorous proof was given by Warshik. Yeah, this is a very nice curve. Yeah, and ST satisfy this equation. Yes, this is the equation of this smooth curve. Yeah, as t goes to infinity, this curve goes to 0, but never touch the t-axis. Yeah, as t goes to 0, s goes to infinity. Okay. That is for uniform case. Uniform case. Next, let's look at the generalized measure. Under this multiplicative measure, beta is bigger than 0. After some properly scale, we have also limiting shape. Limiting shape. The curve looks like this. Okay. This is the curve function. Curve function. Yeah. Here beta is greater than 0. So let's see. So this integral from 0 to infinity is finite. Excuse me.
At beta equals 0, uniform, right?
Beta equals 0 is uniform.
So it'd be the other.
Yeah, yes.
So you could have beta equals 0.
Yeah, beta is not 0 here.
If beta is also
But
reduced
it
to
fits into the previous result.
Yeah. Beta here is beta equals to 0.
Right.
Yeah. Okay. Yeah. Here I want to point out, in this case, two distinct scaling constants must be adapted. In the uniform, the two scalings are the same, 1 over square root n. But in this case, we are using two different scalings in t axis and in s axis. Yeah, the picture looks like this. Under the Plancherel partitions, Zhonggen and sheep and Warshik curve, two different groups got the following limiting curve. Under this case, we use the scaling constant 1 over square root n. Yeah. So here is 2. This point is also 2. So as t goes to goes to infinity, you say. In this case, the limiting curve is represented by a parameter equation. Yeah. Finally, let's look at the asymptotic fluctuations. In the above, we look at the limiting shape, which is a kind of weak law of large numbers. Under some probability measures, we have some weak convergence to a deterministic curve. Now, let's look at asymptotic fluctuations. Yeah, it turns out we should deal with two cases separately. One is at the edge, the other is in the bulk. But in this talk, we just look at, we focus on the bulk, focus on the normal fluctuations. At the edge, it involves extremal law, such as Gumbel law and Tracy-Widom law. Yeah, but in this talk, I don't talk about that. That is another big topic. Yeah, so we have the following central limit theorems for multiplicative partitions. Fix beta bigger than 0. H and beta just 1 over n. The power is 1 over beta plus 2 goes to infinity. We proved that the following central limit theorem. This is the Young diagram. The boundary of Young diagram have functions for lambda minus some constant. This constant mu nt converges plus prime beta t as n goes to infinity. And so we have this limiting distribution. Yeah. And then we also have finite dimensional distribution convergence as follows. For m points t1, t2, tm, so we proved x in t1, x in tm converges in distribution to a normal vector with the covariance structure as this one.
So the Zhonggen distribution could be like Brownian motion or something?
Yeah, looks like that because
This is some transform. If you change the time, looks like Brownian motion.
yeah, you in some sense you're right, but I don't make some transformation to get that.
Because if you change t to the inverse of sigma the function, then covariance becomes h times t.
Mm-hmm.
So that looks like the Brownian motion covariance nature, correlation function.
Yeah, but here I didn't give the explicit formula about the sigma beta of t. So I don't know. Maybe.
Yeah, or maybe just x n of t converges to Brownian motion b of sigma base.
You mean make
sigma square.
some change of time.
Yeah, change of time, yes.
Yeah,
I think that's
Can you just check to see if you have independent increments? With independent increments?
M depends on M.
I mean, look at
the
covariance
covariance
G,
already.
T minus GS and G. Yes. So,
Yeah, GS.
that's not. That's only covariance. Okay.
Yeah, this is the only
I don't
covariance.
think you have independent increments.
No. Sorry. Because beta and beta 1, they're different.
It
Okay.
depends on the definition.
The different. Okay.
Yeah. So here I don't give the exact formula. Okay. At the age, if beta equals 1, we also prove the following two theorems. One, all of these have normal distribution as a limiting distribution, but with a different normalizing constant. And if beta equals 1, we need an extra term, the square root log n. If beta bigger than 1, the normalizing constant looks like this. Yeah. If beta equals 1, that is 1 over 3. But if beta equals 1, we need another term, the square root log n. Any questions, Chima? Okay. Okay. Finally, let's look at the central limit theorem for Plancherel partitions. That is early work. Now let's quickly look at this. Under Plancherel probability measure, for each fixed t, we also a kind of central normalizing and central limit theorem. This is the step function for phenomena. This is the limiting curve plus times the square root n, and then divided by the square root log n, converges in distribution normal random variable. Yeah, the point is the normalizing constant. It is much smaller than the previous theorems. Yeah, we also got a finite dimensional distribution convergence as follows. But here, the limiting random variables are independent of each other. So it is very strange. Yeah, we just consider 2 points. This is T1, this is T2. Yeah, we consider the gap between Young diagram and the limiting curve, and this is 2. So we consider if T1 and T2 are fixed, fixed 2 points. Yeah, the limiting Z1 and Z2 are independent of each other. It doesn't look like the previous one. In the uniform case, in the almost uniform case, the limiting is random variables have this as the covariance structure. Okay. How many times? 5. Okay. Finally, let's quickly look at the basic idea of proofs. The basic idea is to use conditioning argument. But you see, we're talking about 2 different kinds of probability measures. One is uniform, the other is Plancherel. These 2 are different, are very different from each other. So we need to deal with multiplicative partitions and Plancherel partitions separately. In this case, you just think of this as a uniform case. Yeah, if beta is equal to 0, that is uniform. So okay. Now we define a bigger probability space, capital P. Capital P is the set of all partitions of all natural numbers. So we define a probability measure with the parameter Q. Here, looks like this. Under this probability measure, the point is R1, R2, Rk, and so on are all independent random variables. Actually, there are in the uniform case, R1, R2. In uniform case, R1, R2, so on, are geometric random variables, independent. You see, phi lambda t. What is phi lambda t? Phi lambda t is the sum of Rk. K is bigger than or equal to t. So under the PQ, phi lambda t is just the sum of independent geometric random variables. So everything is almost known. We can apply the classical limiting theorems to this sum. Okay, so we can prove the central limit theorems by using characteristic functions or classical central limit theorems to this case. The next question is how to transfer from the bigger space to the small space, from capital P to capital Pn. Okay, that is the following lemma. Basically speaking, PQ is just a combination of measures of measures PM. Yeah, okay. And what is the PM? PM is just a restriction of PQ to capital Pn. So we use this lemma to get the central limit theorems from this case. Okay. quickly. Yeah. Finally, let's look at the Plancherel partitions. We also use a conditioning argument, but here we use another probability measure, p theta. Theta is also a parameter. P theta is just a mixture of pp and a Poisson variables. Under this p theta, we have a nice determinantal structure for lambda I minus I. Lambda I is the part of partition. Lambda I minus I. We have this lemma. This lemma comes from is from Orodin, Oklakov, and Olshansky in 2000 in JMS. This is also famous paper about asymptotics of random partitions. We use this lemma to prove the central limit theorem using Kozdin-Leibowitz central limit theorem for determinantal point process, because this lemma gives us lambda I minus I looks like a determinantal point process. And then we use the technique of Poissonization and de-Poissonization to conclude the proof. So basically speaking, we are using two different kinds of conditioning arguments. Yeah, that's all. Thank you.
Questions or comments?
You get convergence of joint distributions. So after that, usually people ask, why didn't you get the convergence of process?
With the convergence for the
yeah.
process.
So there must be some technical difficulty you can't overcome.
Yes. In this case, you see,
you can,
then we cannot.
Yeah.
We cannot
right.
get a process convergence.
Yeah, but what
Yeah.
about the other one?
The other one, because you say you're in this case, because it is very hard to get uniform tightness. Yeah, for you say for uniform tightness, we need something like xn t1 t2 minus xn t1 square, or r less than t2 minus t1 alpha must be greater than 1.
Yeah.
Okay, for example, we can take r to 2, but we cannot get this this upper bound. We just get here is 1.
Oh.
Yeah, so it is hard to get uniform tightness.
For uniform tightness, of course, you should go to r bigger than 2.
Yes.
Then maybe the first term is 1, so okay. If you have the second term, that's like 2 alpha bigger than 1, how you can prove it. Yeah. I don't know exactly. Then usually you should go to the second term.
You mean here is
Yeah.
second term, maybe 4 or?
Yeah, you should at least you go to 4, I mean, 2 plus something, yeah.
You see, it is possible to calculate the exactly the force moment, because everything is known. Almost everything is known, because R1, R2 are geometric random variables. We need yes, I see. Yeah, we just calculated this. K either the square root t2 bigger than the square root n t1, rk minus e rk, the force or something. Yeah, we get some. Maybe you can get something like 1 minus T2 square plus, we always have some error term, depends on n.
Yeah.
Maybe it looks like 1 over square root of n.
Yeah.
So I don't know how to deal with this case. It is not the standard form.
No, if you have the 1 over square n times the difference, then we know how to find the maximum, especially the maximum force movement. There's some non-lot available. Yeah. So point not be, as long as you can calculate the force movement, you can prove that.
Yeah, the force movement, I think we can.
Yeah.
We can, at least we can estimate this, because you see, the parameter of geometric random variables is known. It's just q, t minus, not this, 1 minus q. Okay, q is the parameter. We usually take qn is equal to the c minus the, and c is a constant. Is always not constant, so it's null. Yeah. Then, oh, by the way, yeah. We're not able to prove the weak convergence for the process, but we can prove the following. F is a test function. If a test function x in t dt converges to f g. Here f is a special class of test function. It's not the you see the set of bounded uniform, bounded continuous function. Yeah, that is the point. Yeah.
In the Plancherel case, in the limit you get some independent Gaussians. I guess that means that you should, maybe the more interesting question will not to take this, different
T1, T2.
Yeah, but
just look at the point T1.
Is it interesting to know how close they should be to get some dependence, right?
Yes, I think you're expert at this area, this field. I think there's some similarity structure. The
eigenvalue of random matrix.
No. Professor Shi looks like consider the fixed t, and then look at the small neighbor of around t. Maybe looks like t plus 1 of n is here is kc.
Yes.
kc and eta are two different constants. Yes. And then we look at the limiting process.
Yeah, that's what.
Yes, we went in 2007. Bogachev, my co-author, and I want to discuss this kind of question, but we didn't. Anyway, we didn't finish that.
Okay, yeah, so that means that
maybe there is some delicate structure around each point t, but for t and t2 different t1 and t2, the limiting random variables are independent. Yeah, that's all.
Okay.
Okay. We have a lot of time here. The next session starts tomorrow morning. Yes, please.
I said I forgot what I was going to say.
So in that case, let's thank all the 3 speakers for the afternoon.